Black holes are not all born from dying stars. Some might be ancient relics, forged in the chaotic first second of reality itself. These are primordial black holes, and their existence would rewrite our cosmic history. By the end of this exploration, you will understand the profound stakes of this hunt, a quest that could finally reveal the true nature of dark matter and expose the physics of the Big Bang. We will sift through decades of ambiguous evidence, from mysterious gravitational waves to unexplained gamma-ray glows, searching for these phantom remnants. Could the key to our universe's greatest mysteries be hiding in the form of invisible, asteroid-sized holes in space? What does our relentless search for such shadows tell us about our own place in the cosmos? This is the cosmic twist that changes everything. A primordial black hole is not a stellar corpse. It is a cosmic fossil, a direct imprint from the universe's violent infancy. Its story begins not in the fiery core of a collapsing star, but in the seething, unimaginably dense soup of matter and energy that existed mere fractions of a second after the Big Bang. Back then, the entire cosmos was a churning ocean of pure potential. Within that ocean, tiny quantum ripples, fluctuations in density, were stretched to enormous scales by the universe's own rapid expansion. Think of it like pulling on a piece of taffy. A tiny, random bump gets stretched into a vast, mountainous ridge. In those first moments, if a region of space became dense enough through this stretching, gravity could have won an instant victory. It wouldn't need a star to collapse. Instead, a lump of the universe itself, a knot of pure density, could have simply pinched off directly into a black hole. This is the key, the fundamental distinction. Stellar black holes are born from the death of a star, an astrophysical event. Primordial black holes are born from the wrinkles in spacetime itself, a cosmological event. Their formation is woven into the very fabric of the expanding universe, making them potential relics of an era no telescope can ever see directly. If they exist, they are not just objects. They are living records of the first second of everything. But for a region of space to collapse into one of these holes, it needed a very specific kind of seed. It needed a flaw, a knot in the fabric. This brings us to the cosmic forge, the place where these seeds were created, and it all hinges on a single, powerful idea: density fluctuations. In the very early universe, space was not perfectly smooth. It was a quantum froth, buzzing with tiny, random variations in energy and density. Picture a pot of water just before it boils. You see tiny bubbles forming and popping at random, a chaotic dance of pressure and heat. The infant universe was like that, but on a scale far beyond our comprehension. Most of these fluctuations were minor, smoothing themselves out almost instantly, but some, purely by chance, were born with a density just a little bit higher than their surroundings. In our universe today, that slight over-density would be nothing. Gravity is a weak force, and matter is spread too thin for it to act quickly. But in that first second, everything was different. The entire cosmos was packed into a volume smaller than a single atom. Matter and energy were unimaginably dense, and gravity could act with terrifying speed. In that environment, a region with even a 1% higher density could have tipped the balance. Its own gravity, pulling inward, could have overcome the outward pressure of the hot radiation trying to blow it apart. It would have been a sudden, silent collapse, no explosion, no light, just a region of space crossing a point of no return, vanishing from the visible universe and leaving behind only its gravitational shadow. But there is a problem. For these random quantum ripples to grow large and dense enough to form black holes of any interesting size, they needed a boost. They needed a mechanism to stretch them from microscopic wrinkles into mountain ranges. That mechanism is the leading theory for the universe's own first growth spurt, a period called cosmic inflation. Inflation proposes that a fraction of a second after the Big Bang, the universe underwent a brief but staggeringly violent expansion, ballooning in size by a factor of trillions upon trillions in less than a blink. This incredible stretching would have taken those tiny quantum ripples and magnified them enormously, imprinting them across the cosmos as the seeds for all future structure, galaxies, clusters, everything. But crucially, it could have also created the perfect conditions for our primordial seeds. If inflation had a slight hiccup, a momentary change in its rate, it could have amplified some fluctuations far more than others. It could have taken a particularly dense knot and stretched it into a region so overwhelmingly heavy that its collapse was inevitable the moment inflation ended and the normal hot Big Bang universe took over. In this view, inflation is not just the reason our universe is so large and smooth. It could also be the very reason it is littered with invisible, ancient traps. The forge was not a gentle one. It was a place of unimaginable violence where the fabric of reality itself was stretched and imprinted with flaws that might still haunt us today. This leads to a truly bizarre possibility, one that stretches our understanding of what a black hole even is. Unlike their stellar cousins, which are all born within a relatively narrow range of masses from collapsing stars, primordial black holes could exist in a staggering spectrum of sizes. They are not bound by the rules of stellar life and death. Their mass depends on a single, simple factor: the precise moment in the early universe when that dense knot of space decided to pinch off and disappear. Form in the first fraction of a second when the universe was at its absolute densest, and you might create a black hole with the mass of a mountain. Form a tiny bit later as the cosmos expanded and thinned out, and you might create one with the mass of an asteroid. Form from a truly colossal fluctuation, and you could theoretically birth a black hole with the mass of 1,000 suns, or even 1,000,000. The scale is almost incomprehensible. We are talking about a potential population ranging from objects lighter than a small moon to entities that could rival the supermassive giants at the center of galaxies. This is not science fiction, it is a direct prediction of the physics. If the conditions were just right, or perhaps just wrong, the infant universe could have acted like a cosmic sieve, creating black holes of every conceivable size, each one a frozen snapshot of the density of the cosmos at the instant of its birth. So the hunt is not for one type of monster. It is for an entire hidden zoology of gravitational ghosts, from specks of invisible sand to leviathans drifting between the stars. And this raises an immediate and thrilling question. If they are out there in such a wild variety of shapes and sizes, how could we possibly hope to find something that emits no light? The answer lies in the one thing they cannot hide: their gravity. Gravity is their signature, but it is also their potential undoing. For the very smallest of these ancient relics, a profound and elegant rule of quantum physics dictates they cannot last forever. This rule comes from a mind that spent a lifetime contemplating the edges of black holes, Stephen Hawking. In the 1970s, Hawking performed a breathtaking feat of theoretical physics. He merged the colossal scale of general relativity with the fuzzy, probabilistic world of quantum mechanics, and he discovered something startling. Black holes are not completely black. Due to quantum effects occurring right at the precipice of their event horizons, they should slowly leak energy, emitting a faint whisper of particles now known as Hawking radiation. For a massive black hole, like one born from a star, this process is unimaginably slow. It would take longer than the current age of the universe to lose even a fraction of its mass. But the smaller the black hole, the faster it evaporates. The intensity of Hawking radiation increases dramatically as mass decreases. This leads to a critical, defining threshold for our hunt. Hawking calculated that any black hole with a mass less than about 1 billion metric tons would have completely evaporated by now, over the 13.8 billion year history of the cosmos. To put that in perspective, 1 billion metric tons is roughly the mass of a small mountain. So, Hawking radiation acts as a cosmic filter. It tells us that if primordial black holes exist today, they must be survivors. They must have been born with a mass above that critical line. Any smaller ones, the truly microscopic black holes that might have formed in the very first instance, are long gone, having presumably evaporated in a final, silent flash of particles. This sets a firm lower limit for observers. We are not searching for specks of quantum dust. We are searching for the resilient ones, the ancient giants that started with enough bulk to withstand the slow erosion of quantum evaporation. Their continued existence, if we find them, would be a testament to their initial heft, a direct clue about the specific conditions in that first fraction of a second. The hunt, therefore, narrows its focus to objects with the mass of an asteroid or greater, shadows that have stubbornly persisted since the dawn of time. This elegant evaporation theory does more than just set a search boundary. It points us toward a truly monumental possibility. What if the survivors, those asteroid-mass black holes and larger, are not just cosmic curiosities? What if they are the hidden architecture of the universe itself? For decades, astronomers have faced one of the most profound mysteries in all of science: dark matter. We see its gravitational grip on galaxies. We map its vast cosmic web, but we have never directly detected what it is made of. The leading candidates have been exotic new particles, theoretical entities like WIMP that require physics beyond our current understanding. But there is another, strikingly simple idea that has endured for half a century. Perhaps dark matter is not a sea of invisible particles at all. Perhaps it is a swarm of ancient, invisible holes. Primordial black holes fit the dark matter profile with an almost eerie perfection. They are massive, so their gravity influences the motion of stars and galaxies. They are compact, so they would not readily collide or dissipate. And most importantly, they are dark, emitting no light we can easily detect. They would be the ultimate cosmic ghosts, drifting unseen through the voids between stars, their collective gravity shaping the cosmos from the shadows. This idea carries a powerful historical weight. It was first proposed seriously in the 1970s, around the same time Hawking was working on his radiation theory. For a while, it was a compelling alternative to the particle hunt. But then, observations seemed to rule it out. If dark matter were made of black holes around the mass of our Sun, they would frequently pass in front of distant stars, causing a telltale brightening called gravitational microlensing. Early surveys looking for these events saw far fewer than expected, seemingly dooming the idea that such black holes could be the dominant form of dark matter. The hypothesis retreated into the background, a fascinating footnote as the search for particles accelerated. Yet, like a resilient seed, it never fully died. Because those early observations only ruled out a specific range of masses, primarily those similar to stars, they said nothing about black holes much smaller or much larger. The door was never completely closed, just narrowed, and in recent years, with new gravitational wave discoveries and more sophisticated sky surveys, that door has been pushed open once more. The modern resurgence asks a more nuanced question. Maybe primordial black holes are not 100% of dark matter, but what if they are a fraction of it? What if the dark universe is not a monolithic entity, but a mixed population with ancient black holes making up a significant portion, especially in certain mass ranges that earlier searches missed? This shifts the entire paradigm. We are no longer looking for a single, magical particle. We are hunting for an entire hidden ecosystem of gravitational fossils. And their discovery would solve two of cosmology's greatest puzzles at once: the origin of primordial black holes and the nature of the invisible glue holding galaxies together. The stakes of the hunt, therefore, are not just academic. They are foundational to our understanding of what the universe is actually made of. The search for these gravitational ghosts began not with a telescope pointed at darkness, but at light. Astronomers realized that if a massive, compact object like a primordial black hole drifted through the galaxy, its gravity would act as a natural lens. According to Einstein's theory, massive objects warp the fabric of space-time, bending the path of light that passes near them. If such an object passed directly between Earth and a distant star, that warping would focus the star's light, causing a temporary, characteristic brightening. This phenomenon is called gravitational microlensing. It does not require the lens to emit any light of its own. It only requires gravity and motion. For a brief window, a dark object could betray its presence by magnifying the light of a star far behind it. This became the first great hunt. In the 1990s, teams of astronomers launched ambitious projects to stare at dense fields of stars, monitoring their brightness night after night, year after year, waiting for the telltale flicker. The most famous of these was the MACHO project. Its name stood for Emassive Compact Halo Objects, a broad category that included not just potential black holes, but also other dark planet-sized bodies. The team chose a brilliant target, the Large Magellanic Cloud, a small satellite galaxy of our Milky Way visible from the southern hemisphere. They monitored millions of its stars, knowing that if our galaxy's halo was indeed packed with dark compact objects, they would frequently drift in front of these background stars, creating a forest of microlensing events. It was a patient, statistical fishing expedition in a cosmic ocean. The results, after years of painstaking observation, were profound yet deeply ambiguous. The MACHO project did see microlensing events. They confirmed that dark, compact objects were indeed out there, drifting through the galactic halo, but the critical number, the rate of these events, was far too low. If primordial black holes of roughly stellar mass made up all the dark matter, the team should have seen hundreds of events. They saw only a handful. This was a landmark conclusion. It decisively ruled out the simplest, most appealing idea that all dark matter could be explained by black holes in that specific mass range. The universe, it seemed, was not teeming with sun-sized primordial holes. For many, this felt like the end of the road for the hypothesis. The elegant idea had collided with hard data and seemingly lost. Yet, a closer look revealed a crucial nuance. The results did not say primordial black holes did not exist. They said they could not be the sole answer. They might still be out there, a minority population, or they might exist in masses the survey could not detect. The microlensing hunt had drawn a line through one part of the map, declaring it empty. But the vast territory of possible black hole sizes, from asteroid mass to thousands of suns, remained almost entirely unexplored. The first great hunt had narrowed the mystery, not solved it. The microlensing results had drawn a clear line, but the map of possibilities was still vast and mostly blank. Then, in 2015, the entire field of astronomy was shaken by a sound. It was not a sound heard with ears, but a ripple felt by instruments so precise they could detect a distortion in spacetime smaller than the width of a single atomic nucleus. The LIGO Observatory, along with its European partner Virgo, had made the first direct detection of gravitational waves, the ripples in the fabric of reality predicted by Einstein a century before. The source, two black holes spiraling together and merging in a cataclysm over 1 billion light-years away. This was not just a new discovery, it was a new sense. Humanity, for the first time, could hear the universe. The initial detection was monumental, but as more and more of these cosmic collisions were heard, a pattern emerged that contained a fascinating puzzle. The black holes involved were not always what astronomers expected. According to our understanding of stellar evolution, the collapse of a massive star should not produce a black hole with a mass much greater than about 50 times that of our Sun. The physics of that violent death, the supernova explosion, tends to blow away too much material. Yet, LIGO and Virgo began hearing mergers involving black holes with masses of 60, 70, even 80 solar masses. These objects were sitting in a theoretical no-man's land, the so-called upper mass gap, where stellar black holes were not supposed to exist. It was as if we had discovered a population of bears larger than any biology textbook said was possible. Where did these unexpectedly heavy black holes come from? This is where the old idea of primordial black holes came roaring back into the spotlight. A stellar black hole faces a ceiling, limited by the messy physics of a dying star. But a primordial black hole faces no such restriction. It is born from a knot in spacetime itself, and that knot could have been almost any size. A primordial black hole with a mass of 80 suns would be no more unusual in principle than one with the mass of a mountain. They are all products of the same ancient process, just frozen at different moments. So, the gravitational wave signals presented a compelling new candidate. Perhaps some of these merging pairs, especially the heavier ones, were not the descendants of stars at all. Perhaps they were primordial binaries, two ancient relics that had been orbiting each other in the darkness since the dawn of time, finally coming together and ringing space-time like a bell. Think of it this way: if primordial black holes were indeed forged in large numbers in the early universe, they would not have been born in isolation. The dense fluctuations that created them would have naturally produced them in clusters. Some of these ancient black holes could have formed gravitationally bound pairs, a cosmic dance set in motion over 13 billion years ago. Isolated from the light of stars, these pairs would have slowly, inexorably lost orbital energy by emitting the very gravitational waves we are now detecting, drawing closer and closer across the eons. Their merger today would be the final, silent chapter of a story that began in the first second of everything. The gravitational wave observatories, then, are not just listening to stellar deaths. They might be eavesdropping on the final moments of the universe's oldest fossils. This possibility has transformed the hunt from a search for quiet, solitary shadows into a search for ancient, dueling ghosts, whose collisions send whispers across the cosmos that we are finally learning to hear. Yet the echoes of these ancient collisions are not the only clues we have. To truly corner these cosmic phantoms, we must look to an even earlier time, to the first few minutes of the universe itself. This is the era of Big Bang nucleosynthesis, the moment when the cosmos cooled just enough for protons and neutrons to fuse into the first atomic nuclei, forging the lightest elements in existence. The universe was a nuclear furnace, and the recipe it followed was exquisitely precise. The amounts of hydrogen, helium, and a trace of deuterium it produced were determined by a delicate balance of temperature, density, and the rate of expansion. This process left behind a cosmic fingerprint, a set of primordial element abundances that we can still measure today in the oldest clouds of gas. And this fingerprint is our most powerful constraint. It tells us what the conditions must have been like during those first critical minutes. Any significant deviation from those conditions would have altered the recipe, changing the amounts of helium or deuterium we see. This is where primordial black holes enter the picture, not as objects we see, but as potential spoilers of this ancient process. If they existed in large numbers back then, they would have been an invisible but gravitationally potent component of the early universe. Their presence would have changed the expansion rate, altering how quickly the universe cooled, and thus changing the outcome of those first nuclear reactions. Even more dramatically, the very smallest black holes, those below the survival mass, would have been evaporating violently during this era through Hawking radiation. That evaporation is not a gentle process. It is a sudden, intense release of energy and particles, a burst that would have injected chaos into the smooth, hot soup of the early cosmos. Think of trying to bake a perfect, delicate cake while someone is randomly tossing firecrackers into the oven. The result would be a mess. In the same way, a large population of evaporating black holes would have scrambled the careful nuclear physics, overcooking some elements and undercooking others. The fact that we observe the ancient elemental abundances to match our theoretical predictions so perfectly tells us something profound. It tells us that the early universe was not littered with such explosive events. It places a severe mathematical limit on how many primordial black holes could have existed, especially in the lightest mass ranges. They could not have been so numerous that they dominated the energy budget of the cosmos during its first few minutes. This constraint is like finding a crime scene perfectly preserved. The undisturbed fingerprint of the light elements is evidence that no major gravitational or explosive intruder was present. So while the door for primordial black holes remains open, this cosmic crime scene investigation has ruled out whole categories of suspects. It tells us they could not have been everywhere in every size. Their population, if it exists, must be a sparse one, a subtle component woven into the fabric of the cosmos without ever overwhelming its earliest and most delicate operations. But the universe leaves its fingerprints in more than just ancient chemistry. It also leaves a ghostly afterglow, a whisper of light from the very moment it first became transparent. This is the cosmic microwave background, a sea of microwave radiation that fills every cubic inch of space. It is the oldest light we can see, a snapshot of the universe when it was only 380,000 years old, a cosmic baby picture. Unlike any cherished photograph, its pristine condition tells a story. The CMB is remarkably uniform, a smooth tapestry of temperature with only tiny, delicate ripples. Those ripples are the seeds of all future structure, the blueprints for galaxies, but the smoothness is the key. It tells us the infant universe was a remarkably calm and even place. This presents another powerful test for our primordial black holes, because if they were present in large numbers during this early era, they would have been more than just passive lumps of gravity. They would have been active, voracious engines. In the dense, hot plasma of the early universe, a primordial black hole would have acted like a drain. Matter, drawn in by its intense gravity, would have spiraled toward the event horizon, heating up to incredible temperatures through friction and collisions in a process called accretion. This process does not happen quietly. Accretion releases a torrent of energy, a blast of radiation that can ionize and heat the surrounding gas. Think of dropping a red-hot stone into a pond of perfectly still, cold water. The stone sizzles, it steams, it creates violent ripples and bubbles that disturb the calm surface. A population of accreting primordial black holes would have been like a shower of such stones falling into the cosmic pond of the early universe. Their collective energy injection would have reheated and scrambled the delicate plasma, creating hot spots and disturbances in the smooth distribution of matter. And because the cosmic microwave background is a direct imprint of that matter distribution, those disturbances would have left permanent scars on the light. We would see them today as anomalous hot and cold patches, distortions in the otherwise uniform temperature map. This is where our most precise measurements come in. The Planck satellite, a European Space Agency mission, spent years staring at this cosmic afterglow with unprecedented sensitivity. It mapped the temperature of the CMB across the entire sky in minute detail, creating the most accurate baby picture of the universe ever taken. And what did it find? It found a breathtakingly smooth and consistent tapestry. The ripples are there, as predicted, but there are no signs of the widespread, violent scarring that a large population of accreting primordial black holes would have caused. The Planck data, like the evidence from primordial elements, acts as a cosmic veto. It tells us that primordial black holes could not have been numerous and active enough during the universe's first few 100,000 years to leave a mark on its most sacred relic. They could not have been the dominant troublemakers in the nursery. Once again, the data does not say they do not exist. It says they must have been a sparse population, or perhaps they were mostly dormant during this critical period, not actively feasting on the surrounding plasma. Each new constraint is like another brushstroke being wiped from a section of the canvas, revealing more of the true picture underneath. The map of where these ancient ghosts could be hiding grows smaller, more defined, and in many ways more tantalizing. Yet the search is not confined to ancient light or gravitational echoes. It also listens for the silent scream of particles, deep in the heart of our own galaxy. A persistent and mysterious whisper has been detected, one that points toward the most violent processes in the universe. For over a decade, NASA, a Fermi gamma-ray space telescope, has been mapping the high-energy sky, and it has found something peculiar at the very center of the Milky Way. There is an unexplained excess of gamma-ray light, a diffuse, glowing fog of the universe's most energetic photons. Gamma rays are not produced by gentle processes. They are the signature of extreme violence born from particle annihilations, matter crushed by magnetic fields, or the furious edges of black holes. The natural explanation for this glow would be a dense population of spinning neutron stars called pulsars, but the distribution and nature of this gamma-ray fog does not perfectly match that expectation. It left a tantalizing gap in our understanding. For years, a leading hypothesis among theorists was that this signal might be our first indirect glimpse of dark matter itself. The idea was that dark matter particles, if they are their own antimatter counterparts, could be colliding and annihilating each other in the dense core of the galaxy, converting their mass directly into a burst of gamma radiation. It was an elegant possibility, a direct line from a mysterious signal to a fundamental discovery. But science requires us to follow every thread, and another, older possibility began to resurface. What if the signal was not from annihilating particles, but from evaporating fossils? This is where the smallest surviving primordial black holes enter the story. Recall Hawking radiation, the slow quantum evaporation that dooms the tiniest black holes. For a black hole with a mass around that of a large asteroid, this process is not a slow leak. In its final, frenzied stages of evaporation, it becomes a runaway explosion. The black hole's temperature skyrockets as it shrinks, and it begins to emit a torrent of particles and radiation, culminating in a final, brilliant flash of high-energy gamma rays. A single such event would be brief and localized, but what if the galactic center is home to a sparse, ancient population of these asteroid-mass primordial black holes? They would not all be evaporating at the same moment, of course, but over millions of years, a steady trickle of them could be reaching their explosive end of life. Each one, in its final second, would unleash a burst of gamma rays. Collectively, these countless silent detonations scattered across the galactic core could produce exactly the kind of diffuse, unexplained glow that Fermi sees. It is a haunting image, the galactic center not just as a place of a supermassive black hole, but as a cosmic graveyard for the universe's smallest, oldest traps, each one blinking out of existence with a gamma-ray sigh. This interpretation is controversial, as all good mysteries should be. The pulsar explanation remains strong, and the data is complex, but the very fact that primordial black holes provide a viable, alternative explanation for one of modern astronomy's most puzzling signals tells us something important. The hunt has moved from simply ruling them out to actively looking for their potential fingerprints in data we have already collected. We are no longer just searching the darkness for shadows. We are sifting through the light itself, looking for patterns that only ancient evaporating ghosts could have left behind. This silent gamma-ray graveyard points us toward a final, explosive possibility. If the smallest of these ancient relics are still out there, we might not find them by their gravity, but by their death. The final act of a tiny primordial black hole is not a quiet fade. According to Hawking's theory, as it nears the end of its multi-billion-year evaporation, the process accelerates violently. In its last second of existence, the black hole's temperature would soar to billions of degrees. It would become, for a fleeting instant, one of the hottest objects in the universe. All of its remaining mass, equivalent to 1 million tons of matter or more, would be converted directly into an intense, focused flash of high-energy particles and gamma radiation. It would be a cosmic firecracker, a pinpoint detonation of pure energy with the power of a small nuclear bomb, all compressed into a burst of light that could outshine entire galaxies in the highest energy spectrum. This is not a slow leak, it is a spectacular terminal flash. And if such an event happened anywhere within our galactic neighborhood, our instruments should, in theory, be able to see it. This prediction transforms the hunt into a form of cosmic vigil. We are not just looking for ancient, stable objects, we are listening for their final screams. Astronomers have turned specialized observatories toward this task, instruments designed to catch the brief, furious signals from the most extreme events in the cosmos. One such facility is the High-Altitude Water Cherenkov Observatory, or HAWK, located on a mountainside in Mexico. HAWK does not look like a traditional telescope. It is an array of 300 massive water tanks, each one watching for the faint, blue flashes of light created when ultra-high-energy gamma rays strike the Earth's atmosphere. It stares at a huge portion of the sky, day and night, waiting for a sudden, unexplained spike in this exotic light. A signal from an evaporating black hole would be unmistakable. A brilliant, short-lived point of gamma rays appearing from nowhere and vanishing just as quickly, with an energy fingerprint that matches no other known astrophysical source. It would be a ghost signing its own death certificate. So far, the sky has not offered up such a clear, singular event, but the absence of a detection is itself a form of data. It tells us that these terminal explosions must be incredibly rare in our cosmic vicinity. The population of asteroid-mass black holes nearing their end cannot be dense, or our detectors would have been lit up like fireworks by now. This pushes the frontier of the search further out and further into the future. The next generation of space-based gamma-ray telescopes, with even greater sensitivity and wider fields of view, will scan the deeper universe for these elusive final flashes. They will listen for the echoes of the smallest ghosts vanishing into the light from which they came. The final flash of an evaporating black hole is a spectacular but elusive end. Yet for those that survive, their silence becomes a different kind of challenge. Among all the possible sizes these ancient relics could be, one specific range has emerged as a modern focal point, a window where the shadows are deepest and the evidence is most intriguing. This is the asteroid-mass window, spanning from about 10 to the 17th grams to 10 to the 23rd grams. To put that in perspective, we are talking about objects with masses ranging from a modest mountain on Earth all the way up to a small world-like Ceres, the largest object in the asteroid belt. This is not the realm of stellar corpses or supermassive giants. It is the domain of the truly compact and dark, a range that has slipped through the nets of most previous searches. Why is this window so compelling? Because it exists in a sweet spot of cosmic constraints. The microlensing surveys ruled out black holes of stellar mass as the dominant dark matter. The cosmic microwave background and Big Bang nucleosynthesis severely limit how numerous they could have been in the very early universe. But for black holes in this asteroid range, those constraints relax. They are too small and light to strongly lens distant stars in a way early surveys could easily catch. Yet they are too large to have evaporated away via Hawking radiation already. They are, in a sense, the perfect survivors, massive enough to persist but small enough to have evaded our most direct probes. This makes them a prime and still viable candidate to make up a portion, perhaps even a significant portion, of the dark matter holding our galaxy together. The hunt, therefore, has sharpened its focus on this specific mass range. But how do you find an invisible object with the mass of a mountain, drifting in the vast darkness between the stars? Its gravity is profound, but its size is subatomic. A black hole of this mass would have an event horizon smaller than a single proton. You could hold the entire mass of Mount Everest in a space tinier than an atom. This presents an almost absurd detection challenge. It will not lens a star brightly enough for traditional surveys. It is not colliding in pairs to make gravitational waves LIGO can hear. We must think smaller and more cleverly. One audacious proposal looks not to the sky but beneath our feet. Imagine a primordial black hole in this mass range passing through the Earth. It is so incredibly tiny that it would zip through our planet like a ghost through a wall, interacting with almost nothing. But almost nothing is not absolutely nothing. Its intense gravitational field would tug on the atoms it passes near. As it travels through the dense rock of the planet, that tugging would create a minuscule vibration, a whisper of seismic energy. The idea is to use the entire planet as a detector, a global network of incredibly sensitive seismometers. The same instruments that listen for earthquakes could in theory pick up the unique signature of such a passage, a subtle tremor moving in a straight line through the planet's interior, unmatched by any known geological process. It is a breathtaking concept, turning our world into a colossal antenna for gravitational phantoms. Another approach aims for even greater precision, moving to the realm of the nanoscale. Researchers have proposed creating exquisitely sensitive sensors using levitated microscopic spheres or even single atoms, held in place by lasers in a near-perfect vacuum. The plan is to monitor these tiny systems for an inexplicable, sudden jolt. If a primordial black hole of asteroid mass passed through the laboratory, its gravitational pull would impart a minute but calculable acceleration to the sensor, a tiny kick that nothing else could explain. These are not instruments that exist at scale today, but they represent the frontier of the hunt where quantum technology meets cosmology. We are no longer just building bigger telescopes. We are engineering quieter rooms, more sensitive ears, and turning entire planets into traps for shadows. The goal is to catch a ghost not by the light it blocks, but by the almost imperceptible ripple it leaves in the fabric of the world around us. While the smallest relics whisper through seismic sensors, their larger cousins could rewrite galactic history with a single, devastating pass. We must now consider primordial black holes not as mountain-sized phantoms, but as potential behemoths with masses ranging from hundreds to tens of thousands of times that of our Sun. These are the intermediate mass black holes, objects that have long been a missing link in cosmic evolution, and their primordial origin offers a startling explanation. If such a monster were drifting unseen through the halo of our galaxy, its passage would not be subtle. It would be a gravitational wrecking ball, leaving scars across the cosmos that we might finally be learning to read. The most telling evidence could be written in the motions of ancient star clusters, the serene and densely packed globular clusters that orbit our galaxy like distant, glittering swarms. These clusters are delicate gravitational ecosystems held together by the mutual pull of hundreds of thousands of stars. They are ancient, stable, and predictable. But introduce a single, invisible interloper with the mass of 1,000 suns, and that stability shatters. As a wandering intermediate mass black hole plows through or near such a cluster, its immense gravity acts like a tidal force. It doesn't need to make a direct hit. Simply passing nearby would be enough to violently stir the cluster's stellar population. the black hole's pull would fling stars out of the cluster entirely, creating faint, trailing streams of stars like the wake of a ship passing through calm water. Even more telling, it would impart a distinct signature to the motions of the stars that remain, leaving them with peculiar velocities and orbits that betray the recent trauma. Astronomers are now conducting cosmic forensic scans, using powerful telescopes to map the precise speeds and trajectories of stars within these ancient clusters. They are looking for the kinematic fingerprints of a past encounter, the subtle evidence that the cluster's serene appearance is a mask hiding a violent brush with a ghost. The search extends beyond globular clusters to the faint, diffuse dwarf galaxies that also orbit the Milky Way. These are galaxies in their own right, but with far fewer stars, making them even more vulnerable to gravitational disruption. A close encounter with a massive, dark intruder could stretch and distort them, pulling stars away into long, arching ribbons known as stellar streams. Our own galaxy is adorned with such streams, the torn apart remains of smaller galaxies that ventured too close to the Milky Way's might. But some streams show peculiar kinks and density variations, features that are difficult to explain by the smooth tidal pull of the Milky Way alone. Could these be the claw marks of a primordial black hole, a dark predator passing through and twisting the stream with its concentrated gravity? This is the new frontier of the hunt, a shift from listening for whispers to surveying the cosmic landscape for signs of a struggle. By meticulously charting the paths of millions of individual stars within streams and clusters, researchers are creating a dynamic map of our galactic neighborhood. Any anomaly in this map, a cluster of stars moving in an unexpected way or a stream with a strange bend, becomes a potential clue. It is a painstaking process, sifting through vast amounts of data to find the one pattern that cannot be explained by visible matter alone. Finding such a scar would be more than just the detection of another black hole. It would be a revelation about the hidden architecture of the dark matter halo itself. It would suggest that the invisible glue holding galaxies together is not a perfectly smooth cloud of particles, but a landscape dotted with these ancient, massive knots of gravity, each one a silent witness to the universe's first and most violent moments. But the most profound impact of these ancient relics may not be written in our own galaxy's scars, but in the very first light we see from the edge of time. This brings us to one of the most urgent puzzles in modern cosmology, the mystery of the impossible giants. Our most powerful telescopes, like the James Webb Space Telescope, are now looking back to when the universe was less than 5% of its current age. And what they find is astonishing, fully formed galaxies, and at their hearts, supermassive black holes already weighing billions of times the mass of our Sun. This presents a monumental problem of time. According to our standard models, a black hole seed, perhaps from the collapse of a single massive star, should need to feed continuously at a breakneck pace for nearly the entire age of the universe to reach such colossal sizes. Yet here they are in the cosmic toddler years, already grown to maturity. It is like walking into a nursery and finding a fully grown adult. The universe, it seems, did not have enough time to grow these monsters from ordinary seeds. Something must have given them a colossal head start. This is where the primordial black hole hypothesis offers its most elegant and sweeping solution. What if the seeds were not born small? What if they were born huge? Imagine a primordial black hole not with the mass of a mountain, but with the mass of 10,000 suns, or even 100,000, forged directly in the furnace of the first second. This is not a stellar corpse, it is a cosmic titan from day one. Such an object would be a primordial intermediate mass black hole, a ready-made gravitational anchor placed into the infant universe. With this kind of massive seed already in place, the growth problem vanishes. A black hole weighing 10,000 solar masses has a much larger appetite, a stronger gravitational pull to draw in the surrounding gas and dark matter. It does not need to start from scratch. It begins life as a dominant force in its region, a gravitational pit around which the first proto-galaxies could rapidly assemble. Its growth from there, while still prodigious, becomes a far more plausible race against the clock of the early cosmos. This idea transforms primordial black holes from mere components of dark matter into the possible architects of cosmic structure itself. They would be the hidden foundations upon which the first galaxies and their central giants were built. The supermassive black holes we see lighting up the early universe with their brilliant quasars might not be puzzles but logical outcomes. They are the descendants of the densest knots in the primordial fabric, the ones that won the cosmic lottery at the very beginning, granting them a legacy of unimaginable gravitational power. Their early existence is not a crisis for our models, but a clue, a fingerprint pointing back to the violent, inflationary conditions that might have sown these massive seeds across the newborn cosmos. The search for these ancient architects requires a detector of almost impossible scale. We must listen not to the collisions of stellar remnants, but to the slow, grinding dance of the universe's heaviest objects, a rhythm measured in decades rather than seconds. This is the domain of the nanohertz, a frequency so low it is more like a cosmic tide than a wave, and to hear it, astronomers have built a clock that spans the galaxy. They call it a pulsar timing array. At its heart are millisecond pulsars, the universe's most precise natural timepieces. These are the spinning cores of dead stars, beaming out flashes of radio light with a regularity that rivals our best atomic clocks. A typical millisecond pulsar might spin hundreds of times per second, and its pulse arrives at Earth with a predictability measured in billionths of a second over years. These pulsars are our lighthouses scattered across the galactic ocean. By meticulously monitoring the arrival times of these pulses from dozens of these pulsars for years, even decades, scientists can detect when something subtly alters their rhythm. If a pulse arrives a few billionths of a second early or late, it is a clue. That minuscule shift could be caused by the pulsar itself moving slightly, nudged by the passage of a gravitational wave stretching and compressing the space between it and us. But one pulsar's anomaly could be a local glitch. The true signal emerges from the correlation of anomalies across many pulsars spread across the sky. A genuine gravitational wave passing through our galaxy would affect all of them in a coordinated pattern, a specific fingerprint in the timing noise. This network of celestial clocks becomes a single, galaxy-sized interferometer, sensitive to gravitational waves with periods of years to decades. This is the nanohertz band, a frontier of gravitational wave astronomy completely inaccessible to ground-based detectors like LIGO. And what could possibly create such long, slow ripples in spacetime? The leading candidate is the slow, in-spiral of the most massive binaries in the universe, pairs of supermassive black holes at the centers of merging galaxies. But here is where the primordial hypothesis whispers again. If a significant portion of dark matter, or those early galaxy seeds, were primordial black holes of staggering mass, they too could have found each other in the darkness. A population of these supermassive primordial binaries, orbiting each other over cosmic eons, would fill the universe with a faint, overlapping hum of nanohertz gravitational waves. It would not be a distinct chirp but a stochastic background, a gravitational murmur underlying everything, like the distant, collective roar of a crowd heard from far away. In recent years, the major international pulsar timing array collaborations have all reported the same tantalizing hint. Their decades of data show a low-frequency rumble, a common signal affecting all their pulsars in just the way a gravitational wave background should. It is not yet a confirmed detection of any specific source, but it is a persistent hum in the data that grows stronger with each passing year of observation. The exciting possibility is that we are beginning to hear this cosmic murmur. while the most likely explanation remains a chorus of ordinary supermassive black hole binaries from galaxy mergers. The signal's specific characteristics, its amplitude and frequency spectrum, will eventually tell a more detailed story. Could part of that hum be the collective voice of ancient primordial pairs, dancing since the beginning of time? The pulsar timing arrays are now listening closely, their galactic scale ears tuned to the slowest rhythms of reality, seeking the deep bass note that might finally reveal the ghosts woven into the foundation of everything. Inflation provides the most elegant and popular cosmic forge, but it is not the only crucible in the theoretical arsenal. The extreme energies of the first second allowed for phenomena so alien they challenge our intuition, each offering a different pathway to create these ancient shadows. One compelling alternative focuses on a moment when the universe underwent a fundamental change of state, like water freezing into ice. This is the idea of a cosmic phase transition. As the hot, expanding universe cooled, it may have passed through several critical thresholds where the forces and particles we know today condensed out of a more symmetric, unified state. The most dramatic of these could have been the quantum chromodynamic, or QCD, transition. This was the moment when quarks, the fundamental building blocks of protons and neutrons, ceased roaming freely and became permanently confined within those particles. Think of it like a sudden rainfall condensing from a saturated fog. During that turbulent process, the cosmos could have become lumpy. Regions of slightly higher density might have formed as the new state of matter emerged, and if some of those lumps were dense enough, they could have directly collapsed. The fascinating consequence here is scale. Because this transition happened at a specific temperature and time, it would naturally produce black holes within a narrow range of masses, potentially around the mass of our Sun. This gives a clear, testable prediction, a spike in the population at a specific point on the mass spectrum, unlike inflation's broader possibilities. Another exotic factory involves defects in spacetime itself, remnants of earlier phase transitions that became frozen into the fabric of the cosmos. The most famous of these are cosmic strings. These are not strings in any ordinary sense. They are theoretical, unimaginably thin filaments of pure energy, thinner than a proton but with the mass of a mountain range per inch, left over from the universe's first moments. They would form a tangled network stretching across the cosmos, and under the right conditions, loops of these cosmic strings could collapse under their own immense tension, their energy concentrated into a point so dense it forms a black hole. This mechanism would also produce a distinctive signature, a spectrum of black hole masses tied to the properties of the strings themselves. The vision is startling, the universe's first moments leaving behind not just wrinkles, but cracks in reality that could knot themselves into gravitational traps. Perhaps the most visually dramatic scenario involves bubbles. In some models of the early universe, different regions could have undergone phase transitions at slightly different times. A region that transitioned earlier would be like a bubble of the new, more stable state of the universe, expanding at nearly the speed of light into the surrounding, older, unstable state. When these rapidly expanding bubbles eventually collided, the walls of the bubbles, regions of concentrated energy, could have released titanic amounts of force in focused regions. That concentrated energy in the collision zone could have been sufficient to warp space itself into a black hole. This process would likely create black holes that are both massive and born in clusters, from the chaotic froth of colliding domains in the newborn cosmos. Each of these theoretical crucibles, from freezing fields to snapping strings and colliding bubbles, offers a different origin story and a different predicted fingerprint. They remind us that the hunt is not for one thing, but for a clue that could tell us which of these unimaginable events, if any, actually shaped the hidden foundations of our reality. The faint hum of nanohertz waves points toward massive, ancient dances, But to find the smallest survivors, we must look for a different kind of ripple, one measured in the briefest flashes of the highest energy light. This brings us to one of the most delicate and speculative ideas in the entire hunt, a method that uses the universe's most violent explosions to illuminate its smallest possible shadows. It is called Femtolensing, and it is a concept that pushes the limits of both theory and observation. To understand it, we must first consider the nature of light itself. Light is a wave, and like any wave, it can be bent and focused by gravity, which is the principle behind gravitational lensing. But when the lens is incredibly tiny, like an asteroid-mass primordial black hole with an event horizon smaller than a proton, something extraordinary happens. The lens does not simply magnify the light source, it splits the light wave, forcing it to travel along two slightly different paths around the gravitational pit before recombining. When waves recombine, they interfere with each other. If the peaks of the waves align, they amplify each other, creating a bright spot. If a peak meets a trough, they cancel each other out, creating a dark spot. This creates an interference pattern, a signature of wave behavior. For this effect to be visible, the lens must be comparable in size to the wavelength of the light being lensed. This is why femtolensing is so named. It deals with lenses on the scale of femtometers, or quadrillionths of a meter. The only cosmic light with wavelengths that short is the most energetic gamma radiation. And the only events that produce such brilliant, brief flashes of these gamma rays are the most catastrophic explosions in the universe, gamma-ray bursts. Now imagine a scenario. A titanic gamma-ray burst detonates in a distant galaxy, sending a furious pulse of light across the cosmos. Somewhere along its billion light-year journey to Earth, that flash of radiation passes close to a solitary, asteroid-mass primordial black hole drifting silently in the intergalactic void. As the gamma rays skirt the black hole's intense gravity, the wave is split. The two paths converge again by the time they reach our telescopes. The result would not be a simple brightening. Instead, the energy spectrum of the gamma-ray burst, when broken down with exquisite precision, would show a distinct, oscillating pattern, a series of peaks and valleys in intensity across different energy bands. It would be a fingerprint of wave interference imprinted on the most powerful explosion known, a ghost signature written in the briefest flash of the highest energy light. The beauty of this method is its theoretical cleanliness. If such a pattern were found, it would be incredibly difficult to explain by any other astrophysical process. It would be direct evidence of a compact, massive object along the line of sight, and the scale of the interference would precisely reveal the mass of the lens, down to the asteroid mass range we are so interested in. The challenge, however, is staggering. It requires a near-perfect alignment between the burst, the black hole, and our detector, a cosmic coincidence of breathtaking unlikelihood. It demands that we capture the full, detailed energy spectrum of a gamma-ray burst in the fleeting seconds it is visible, with instruments sensitive enough to discern the subtle interference ripple within the data. And we must rule out every other possible source of spectral variation, from the complex physics of the burst itself to absorption by intervening gas clouds. It is like trying to detect the shadow of a single grain of sand by the way it distorts the flash of a camera bulb from miles away, while the bulb itself is exploding in a chaotic fireball. No confirmed detection has ever been made, and perhaps none ever will. Yet, the very fact that this idea exists on the whiteboards of theorists tells us something profound about the hunt. We are not just building bigger detectors, we are learning to read the fine print of the cosmos. We are looking for ghosts not by the space they occupy, but by the way they subtly comb the light that passes through them. It represents the ultimate in precision cosmic forensics, searching for the most minuscule of defects in the fabric of reality, using the universe's own most brilliant flashes as our microscope. The search for the smallest of these relics leads us to a startling and deeply speculative possibility, one that shifts the hunt from the cosmic scale to the ground beneath our feet. If an asteroid-mass primordial black hole with an event horizon smaller than a proton were to pass through a planet or a moon, its journey would be almost perfectly ghost-like. Yet almost is the critical word. While the black hole itself would zip through solid rock as if it were empty space, its immense gravity would not be so subtle. Every atom along its path would feel a tremendous, instantaneous pull toward that microscopic point. For a fleeting moment, each atom in a straight line through the planetary body would be accelerated to incredible speeds, only to slam back into the surrounding material as the black hole moved on. The result would not be a cavern or a tunnel. It would be something far stranger, a needle-thin filament of ultra-dense, shock-forged material. Think of it like dragging a supersonic needle through a block of clay. The needle passes through without leaving a hole, but the violent compression along its path fuses the clay into a hard, dense line. On a planetary scale, this could leave a geological oddity, a long, perfectly straight deposit of minerals compressed to an impossible density, buried deep within the crust or mantle. It would be a fossilized scar, not from an impact on the surface, but from a ghost passing through the heart of the world. This idea lies on the fringe of cosmology, a fascinating thought experiment that bridges the unimaginably ancient with the geological record. Proponents of the idea sometimes point to enigmatic geological formations as potential candidates, long, linear structures of unusual composition that defy easy explanation by conventional tectonics or volcanism. Could some of these be the ancient wounds of a primordial black hole's passage, events that might have occurred hundreds of millions of years ago? The concept forces us to look at our own planet with new eyes, to consider whether the very rocks hold evidence of a visitor that was not a rock at all, but a knot of pure gravity from the dawn of time. Yet science demands we hold such thrilling ideas against the harsh light of more conventional explanations. The Earth is a dynamic, violent place. Plate tectonics grinds continents together, volcanic plumes punch through the crust, and asteroid impacts of unimaginable force have scarred its surface repeatedly. The processes we understand can create an astounding array of strange geological features. A long, dense mineral deposit could be the remnant of an ancient dike, where magma forced its way into a crack and solidified. It could be the result of extreme pressure and heat along a fault line, or the product of a highly focused, long-lived hydrothermal vent. The history of our planet is written in chaos and slow, relentless change, offering a rich catalogue of explanations that do not require exotic physics. This is the essential tension at the heart of the hunt. The most extraordinary claim demands not just a curious anomaly, but a signature that is truly impossible to replicate by any known geological means. A primordial black hole scar would need to be mathematically perfect, a line of material with a density and composition profile that matches the precise simulation of a gravitational needle moving at cosmic speeds. It would need to be found in a context that rules out every other earthly process. To date, no such smoking gun has been identified. The power of this idea, therefore, is not in providing an answer, but in expanding the landscape of questions. It reminds us that the evidence for the universe's first moments might be hidden in the most unexpected places, waiting to be read not in the light from distant quasars, but in the silent, compressed stone beneath our feet. It turns the entire Earth into a potential detective, a recorder of ghostly passages across the eons. This search for ghosts is also a hunt for echoes in a digital universe. While astronomers scan the skies with telescopes and physicists listen with gravitational wave detectors, another critical search is happening entirely inside supercomputers. Theorists are building entire cosmos from scratch, running vast simulations of the early universe to understand where and how primordial black holes could have formed, and what marks they would have left on everything that followed. These are not simple animations, they are complex mathematical universes governed by the equations of general relativity and quantum field theory, running on some of the most powerful machines ever built. The goal is to rewind time to simulate the conditions of the first second under different assumptions. What if inflation had a sharp feature, a sudden change in its energy landscape? What if the universe underwent a violent phase transition like water suddenly freezing? By tweaking these initial conditions in their digital models, scientists can watch what happens. They can see if dense regions form, and if those regions become dense enough to collapse under their own gravity, creating a population of primordial black holes. Each hypothetical scenario, each tweak to the physics of inflation, produces a different statistical fingerprint. One model might predict that primordial black holes are all roughly the same mass, a specific spike on the cosmic scale. Another might predict a broad spectrum, from tiny mountain mass objects to giants weighing thousands of suns. Crucially, these simulations also predict how these black holes would be distributed. Would they be scattered randomly through space like solitary hunters, or would they be born in dense clusters, gravitationally bound to each other from the very beginning? This clustering is a key signature. If primordial black holes made up a significant part of dark matter, their gravitational pull would have influenced how ordinary matter clumped together in the early universe. They would have acted as seeds around which the first stars and galaxies formed slightly earlier, or in slightly different patterns, than in a universe where dark matter is a smooth sea of particles. This is where the digital hunt meets the observational one. The predictions from these supercomputer universes create a target list for real-world telescopes. Astronomers conducting massive galaxy surveys, like the Dark Energy Survey or the future Vera-C Rubin Observatory, are mapping the precise three-dimensional positions of billions of galaxies across cosmic history. They are looking for subtle statistical anomalies in this large-scale structure, deviations in how galaxies are clustered that might match the predictions of a simulated universe seeded with primordial black holes. It is a process of matching fingerprints. The simulations say, if primordial black holes of a certain mass and clustering exist, then the galaxy distribution today should look like this. The observers then take their incredibly detailed maps of the real universe and ask, does it match? So far, no definitive match has been found, which in itself is valuable data. It rules out whole families of theoretical models, narrowing the possibilities for what the early universe could have been like. This computational hunt transforms the search from a fishing expedition into a forensic investigation. We are not just looking for a dark object, we are testing the very blueprints of creation, comparing the architecture of our real cosmos against digital ghosts of what might have been. The ghost will not reveal itself through a single whisper, but through a chorus of voices across the entire spectrum of physics. This is the essence of the multi-messenger future, a strategy that recognizes no single telescope or detector can corner a primordial black hole alone. Their definitive discovery will be a symphony, not a solo. It will come from the powerful synergy of listening to space-time, watching for flashes of light, and mapping the silent architecture of the cosmos all at once. Each method has its strengths but also its blind spots and potential for false alarms. A strange gamma-ray flash could be a pulsar. A peculiar microlensing event might be a wandering star. An odd ripple in a gravitational wave could be a rare stellar collision. But when signals from completely different instruments, observing the universe in radically different ways, all point to the same invisible object with the same properties, the case becomes undeniable. Imagine a police sketch artist working from multiple witnesses. One describes the suspect's height from a shadow, another notes the timbre of their voice from a phone call, and a third captures their fleeting image on a security camera. Combined, these disparate clues create an identity far more reliable than anyone alone. The hunt for primordial black holes is building this exact kind of cosmic forensic profile. Gravitational wave observatories like LIGO and Virgo and the future space-based detector LISA are our ears to the collisions and inspirals of massive objects. They could hear the merger of an intermediate mass primordial black hole binary, a deep thud in spacetime that stellar evolution cannot easily explain. But to confirm it is primordial, we need eyes as well. This is where an instrument like the Vera-C, Rubin Observatory's legacy survey of space and time, comes in. If LIGO hears such a merger, the LSST, with its ability to scan the entire visible sky every few nights, would race to pinpoint the region of space it came from. The crucial test would be to look at that exact spot and see nothing. No glowing wreckage of colliding stars, no supernova remnant, no host galaxy that should have been home to such massive stellar black holes. The absence of light in the place where spacetime rang would be its own powerful testimony, pointing directly to a collision of dark, ancient objects born in the void. Meanwhile, gamma-ray telescopes like the Fermi satellite monitor the sky for the high-energy signatures of evaporating black holes or the distant flashes of gamma-ray bursts that might be femtolensed. A suspicious burst with a strange interference pattern in its spectrum would be a tantalizing clue, but alone it could be a fluke of the burst's own chaotic physics. However, if a pulsar timing array, listening to the slow gravitational wave hum of the universe, simultaneously detected a background rumble consistent with a population of objects at the same mass range, the evidence would reinforce itself. The gamma-ray data would suggest a small, compact lens. The nanohertz waves would suggest many such objects exist collectively. The two messengers, one from the death of the smallest black holes and one from the slow dance of the largest primordial binaries, would paint different parts of the same vast picture. This cross-verification is the ultimate defense against astrophysical mimics. Nature is inventive, and rare stellar phenomena can often masquerade as something new. But it is incredibly unlikely for a mimic to perfectly reproduce a signal seen in gravitational waves, in gamma rays, in optical surveys, and in the timing of pulsars all at once. A true primordial black hole signature would have to be consistent across all these channels, its mass and distance and population statistics agreeing no matter how we choose to look for it. This multi-messenger convergence is what turns a curious anomaly into a foundational discovery. It transforms a ghost story into a chapter in the textbook of the universe. We are no longer just building better detectors, we are weaving them into a single, intelligent net, designed to catch a shadow by how it bends everything that touches it. The final proof will not be a single shout in the dark, but a harmonious echo returned from every corner of our perception. Yet this grand symphony of detection rests on a single, profound assumption that the ghosts are there to be heard. We must confront the other side of the mystery, the possibility that after all our searching, we find only silence. What if primordial black holes do not exist, or are so vanishingly rare they are effectively absent from the cosmos? This is not a failure of science, but a discovery of a different kind, one with consequences just as deep. A definitive, universal non-detection would be a monumental result in itself. It would mean that the early universe was a far smoother, more orderly place than many theories have dared to suggest. The chaotic froth of quantum fluctuations, the violent phase transitions, the snapping cosmic strings, none of them produced a density so extreme it collapsed into an enduring whole. The forge of creation, for all its unfathomable energy, operated with a surprising gentleness, never quite tying a knot in space-time tight enough to last. This silence would act as a cosmic filter, placing incredibly tight constraints on the physics of that first second. Broad, popular classes of inflationary models, those that predict dramatic features or sudden changes in their energy landscape, would be ruled out. The models that survive would be the ones that predict an exceptionally smooth ride, a graceful expansion that magnified quantum seeds just enough to create galaxies, but never so violently that it birthed black holes. It would tell us that the exotic phenomena we theorize about, from colliding vacuum bubbles to networks of cosmic defects, either did not occur or occurred in such a muted way that they left no gravitational fossils behind. The universe's infancy in this light would appear less like a turbulent, creative explosion and more like a precise, calibrated unfolding. A null result narrows the path. It tells us which grand stories about our origin are simply not written into the fabric of reality. This is the power of a negative answer. It clears the board of fascinating possibilities, forcing us to look with even greater precision at the ones that remain. The hunt, therefore, transforms from a search for objects into a test of creation's character. Every empty patch of sky, every unexplained signal that turns out to be something else, every sensitive instrument that hears nothing, is another piece of evidence. It is evidence for a cosmos that chose a path of remarkable smoothness, where the seeds of structure were sown with a delicate hand, and where the dark matter that binds the galaxies must be something even more elusive, a sea of particles so faint they have evaded every earthly detector. In this scenario, the mystery of dark matter deepens, pushing us further toward the frontiers of particle physics. The absence of primordial black holes would make the universe, in a way, more strange, not less. It would mean the invisible majority of everything is made of something fundamentally unlike any matter we have ever seen or touched, a substance that interacts with our world through gravity alone. So the quest does not end with an empty net. It simply changes direction, guiding us toward a different, perhaps even more profound, understanding of what the universe is and what it is not. The value lies not in finding the ghost, but in learning the true nature of the house it was said to haunt. The cosmic crime scene is filled with ambiguous evidence, and every clue has at least two suspects. Take the unexpected black holes heard by LIGO and Virgo, those heavyweights in the so-called upper mass gap. Their gravitational wave chirp is clear, but their origin story is not. On one side of the courtroom sits the primordial black hole hypothesis, arguing these are ancient relics from the first second, naturally born heavy. On the other side stands conventional astrophysics, which must now explain how its own rules could be bent to create such massive stellar corpses. The jury is still out, and the deliberation hinges on a fierce competition between two compelling narratives. The first is the story of hierarchical mergers in dense stellar environments. Imagine a globular cluster, a tight ball of hundreds of thousands of stars. Within such a crowded neighborhood, black holes born from massive stars will naturally sink to the center, forming a dense gravitational dance floor. They pair up, merge, and the new, heavier black hole that results from that collision can then go on to find another partner. Through a chain of successive mergers over billions of years, a black hole could step its way from a typical stellar mass into that forbidden upper gap. It is a slow, violent ballet in a crowded room, and it is a perfectly viable process that does not require new physics, only extreme environments and enough time. The second astrophysical narrative involves pushing the limits of stellar evolution itself. Could a single, incredibly massive star in the early universe, one poor in heavy elements, collapse directly into an 80 solar mass black hole without blowing itself to pieces in a supernova? Some sophisticated models suggest that under just the right conditions, in what is called a direct collapse scenario, it might be possible. The star essentially implodes so completely that little material is ejected, packing nearly its entire weight into the newborn hole. This would be a rare and spectacular stellar death, but not an impossible one. So how do we judge between these established astrophysical pathways and the more exotic primordial one? The evidence is not in the merger event itself, but in the context surrounding it. A key test is location, location, location. A hierarchical merger from a dense star cluster would leave a traceable address. The gravitational wave signal would point back to a known, ancient globular cluster, or at least a region of a galaxy where such dense environments exist. A primordial black hole merger, however, carries no such baggage. These ancient binaries could have formed in the vast, empty dark matter halo, far from the light of any galaxy. They could merge in the emptiness between galaxies, a dark wedding with no stellar witnesses. Therefore, if future gravitational wave events in the mass gap can be pinpointed to empty intergalactic space, the case for a primordial origin grows immensely stronger. Another telling clue will be spin. Black holes born from the collapse of a single star tend to have significant spin, a legacy of their progenitor's rotation. Black holes that are the products of previous mergers, however, can have much lower or even negligible spin, their motion scrambled by the violent collision. If LIGO detects a mass gap black hole with very low spin, it would favor the hierarchical merger story. A primordial black hole, born from a quiet gravitational collapse of a density fluctuation, might also have very little innate spin, making this signature frustratingly degenerate. The breaking point may come from statistics and populations. As we hear hundreds more of these cosmic collisions, patterns will emerge. Does the mass gap fill up evenly, suggesting a broad primordial spectrum? Or do we see a pile up at specific masses, like 60 or 80 suns, which could point to a preferred outcome of stellar evolution or a particular step in the hierarchical merger chain? The rate of these events is also critical. If we hear them far more often than our models of dense star clusters predict, the scale would tip toward a plentiful primordial population. Currently, the evidence leans cautiously toward astrophysics, simply because it relies on known, if extreme, processes. But the door is wide open. Every new gravitational wave detection is another data point, another vote in this cosmic election. The next generation of observatories, both on the ground and in space, will provide the precision needed to read the fine print, to measure spins more accurately, and localize mergers to within a specific galaxy or void. Until then, the mystery thrives in this beautiful tension, where the known universe strains to explain its own outliers, and the ghosts of the first second wait silently in the shadows, their existence hinging on a story written in the language of gravity itself. The search for primordial black holes has become far more than a hunt for a single cosmic phantom. It has evolved into a comprehensive, multi-pronged investigation into the very laws that govern reality. Whether they exist in great numbers or not at all, these hypothetical objects serve as an extraordinarily powerful theoretical probe. They force us to ask the most fundamental questions about the universe's first moments, the nature of gravity, the identity of dark matter, and the origin of cosmic structure. Each experiment that fails to find them is not a failure of science, but a successful narrowing of possibilities, a tightening of the constraints on what the infant cosmos could have been like. This relentless process of elimination is how we map the boundaries of the possible, inching closer to a true understanding of our origins. Ultimately, the value of this decades-long quest may lie less in the destination and more in the journey itself. The drive to find these gravitational ghosts has catalyzed breathtaking technological innovation. To listen for them, we built instruments that can sense ripples in space-time smaller than an atomic nucleus. To see their influence, we created telescopes that map the sky in unprecedented detail and surveys that track billions of stars. To simulate their birth, we push supercomputers to model the entire universe from its first fraction of a second. These are not just tools for one hunt, they are new senses for humanity, expanding our perception of the cosmos in ways that will undoubtedly reveal wonders we have not yet even dreamed of. The story is far from over. The next generation of experiments is already taking shape. the Vera C. Rubin Observatory will soon begin its decade-long scan of the sky, watching for the subtle flickers that might betray a dark lens. The space-based Gravitational Wave Observatory LISA will open a new low-frequency window, potentially hearing the slow in-spiral of primordial black hole pairs that formed in the early universe. Ever more sensitive pulsar timing arrays will continue to listen for the nanohertz hum of the cosmic gravitational wave background. And in laboratories around the world, physicists are devising ever more ingenious methods to catch the faintest gravitational whisper of a passing ghost. Each new tool brings us closer to an answer, so this is an invitation to witness a living scientific mystery. The question of whether the universe is seeded with ancient relics from its birth is one of the great open chapters in our story of the cosmos. Whether the final verdict is a triumphant discovery or a profound absence, it will reshape our fundamental picture of reality. The hunt continues in the data streams of telescopes, in the quiet hum of detectors, and in the collective curiosity of the human mind. The next clue could arrive at any moment, a signal waiting to be decoded, a shadow finally stepping into the light.